Okay, so we talk about quicksort. It is another sorting algorithm. So it is a divide and conquer algorithm. So we in the divide step, so we have given an array of size n and we need to sort it. So what we do? We divide the array into two sub arrays based on a pivot element. So we divide the array into two sub arrays such that the left sub array, all the elements in the left sub array are less than x and all the elements are in the right sub array are greater than x, where x is a pivot element. This is all the elements in the right sub array. So basically we are partitioning the array into two parts. So this is the pivot element. We can take any element of the array as a pivot element, but for our partition algorithm we will take first element as a pivot element. So we choose a pivot element and that is x. So now in this divide step we will be using a partition algorithm, partition subroutine, where it will partition the array into two parts. In the left part all the element must be less than x, and in the right part, right sub array, all the elements must be greater than x. So that is the divide step. So what is in the conquer step? So now we have two sub arrays. Now we sort this sub array recursively. So recursively we sort two sub arrays. We sort the sub arrays. So that is the conquer step. And then what is the combine step? So nothing to combine. I mean, x is in correct position. So this is we are going to sort by recursively. This is we are going to sort by recursively. So no job is left. So nothing to be done here. So done. So we want to have a. So this is the divide and conquer algorithm. So in the divide step we need to have a partition algorithm which will partition the array into two parts. So let us just talk about the partition algorithm of quicksort. So let us just write the pseudo code for partition. Okay, so this is, suppose this is our array from P to Q. Okay, initially it is from n to n, but we will have to recursively call this again and again. So we are taking the general term P to Q, and we choose the first element of the array as a pivot element AP. So we have an array. This is AP to AQ. So we choose this as a pivot element. So that is our x. Now we want to do what? We want to partition this array into two parts such that x will be sitting somewhere here, and then this is all the elements will be here is less than x, all the elements here is greater than x. So let us just try to write the code. So we choose I index as p, and we will be having a loop j p plus 1 to q. And the loop invariant we want is, so this is our loop invariant. So I will be pointing somewhere here at some point of time, and j will be pointing here. So we want all the elements over here must be less than x, all the elements over here must be greater than x, and this is yet to decide. So initially everything is yet to decide. Now we have a loop in j. So if this guy, this is our aj, If aj is greater than x, then we can simply increase j by 1, that will be taken care by this for loop. But the problem is if this guy is less than x, so that we have to fix. So, under this loop, if aj is less than x, then we have a problem. Then we cannot just increase j by 1, because that is not we are looking for. So, what we have to do? So, what is the solution? We cannot increase j by this one, because this is the guy over sitting here is less than x. So, what is the solution? Solution is, we know the guy who is sitting here, this is I, this is I plus 1, I mean a I plus 1. So, we know guy over sitting here is greater than x. So, what we can do? We can swap this and this, and we can increase I by I plus 1 and j by 1, that we are going to do here. So, if this, then we increase I by this, and we exchange ai with aj, and I is increasing here. Now, this was less than, so this is coming here, and j is peacefully can increase by 1. Okay, so this is the code. So, this is for loop. So, after this loop, we will just execute this. So, now finally, what we will do? We exchange ap with ai. So, that I is the, and we return the I. Okay. So, this is the code, this is the pseudo code for partition algorithm for Quicksort. We will take an example. Suppose we have this 6, 8, 3, 4, 9, 5, 7. Suppose this is our given array, and this is P to Q. Okay. So, now we want to execute this code on this given input. So, what we do? We just so what is our x? X is basically 6, which is basically first element of the array we are taking. So, we are starting from I is equal to this, j is equal to this. Now, we execute this. Now, aj is greater than 6, we can peacefully increase j by 1. Now, here aj is less than 6. Now, we got a problem, but we know the here who is sitting here is greater than. So, we increase I by 1 and we exchange 3 and 8. So, 3, 8, 4, 9, 5, 7. So, now I is pointing here and j is pointing here. So, now this is again less than. So, what we do? We just increase I by 1 and we exchange this and this. So, 8, 3, 4, 8, 9, 5, 7. So, now I is pointing here and j is pointing here. So, this is greater than 6. So, no problem, we can just increase j by 1. Okay. So, now we see everything over here are less than x and everything over here are greater than x. So, that is the loop invariant we want. Now, we reach here. Now, we got a problem here. So, what we have to do? We have to increase I by 1 and we have to exchange this and this. So, 6, 3, 4, 5, 9, 8, 7. Now, j is pointing here and I is pointing now this 9. I is pointing this 5. Okay. Now, 7 is greater than, so peacefully done. So, this is our I. So, now we exchange this and this in this step and we put this pivot element here 6 and this is 5 and this is 1, 2, 3, 4. So, we return 4. 4 is the position of the pivot element after this partition algorithm. So, you see here after execution of this. So, we have 6 is our pivot, everything here is less than 6. So, all the elements are 5, 3, 4 and everything over here is 9, 8, 7. So, this is the divide step, and in the conquer step we have to again recursively sort this array, and then done, nothing to combine. So, this is the partition subroutine. So, we have to write the pseudocode for quicksort then. So, what is the time complexity for this code? This is basically a for loop of size n. If our array is n, if p and q in such a way that length is n, then this is a linear time algorithm. So, this is a theta of n time algorithm. So, now we have to write the pseudocode for the quicksort. So, this is A. So, we have to call this quicksort on this array. So, what we do, if p is less than q, then only, otherwise we will return. If p is equal to q, there is only one element, it is sorted, we will just return. So, if p is less than q, then what we do, we call the partition algorithm, partition subroutine on this. Okay. And then we call quicksort, this is the recursive call quicksort. So, this will be, so after partition x is sitting here and this is p to q and this is the r. Now, we have to sort this. So, quicksort A p to r, and again this is to sort the right sub array A r plus 1 to q. So, this is the pseudocode for quicksort, and the initial call is initially our array is from 1 to n. So, initial call is quicksort A 1 to n. Okay. So, this is the pseudocode for quicksort. Now, we have to analyze this algorithm. Analysis of quicksort. So, okay, then, so what is the worst case for quicksort? Because in this version we are taking the first element as a pivot each time. So, what is the worst case? If the array is sorted or reverse sorted. If the array is sorted or reverse sorted, in that case what? In that case, every time our pivot element is the maximum or minimum. So, that means it will, after the partition, it will divide the array into, if it is minimum, this all the elements over here, or if it is maximum, x will be sitting here, all the elements over here. So, it is dividing the array into 0 is to n minus 1. So, which is very bad partition. So, if that is the case, then what is the time complexity? What is the recurrence? So, the recurrence will be, so one, we have nothing in the one part of the array. So, T n is equal to T 0 plus T n minus 1 plus theta of n. This theta of n is for the this partition subroutine, the cost for the partition subroutine, and the divide and the combine, nothing to combine, but this is the cost for divide and combining. This is the basically the time complexity for the partition. Okay. So, this is the recurrence for this worst case when we have choosing the minimum or maximum element each time. So, what is the solution of this recurrence? How to solve it? We can use the recursive tree to solve it. So, T n is basically theta of n, we can just say C n. So, C n T0, then this is again Tn minus 1. So Cn T0, C of n minus 1, T0, C of n minus 2, this is T of n minus 2 like this, T0 like this. So this will stop at T0 again. So this sum itself is, so the total time complexity is the sum of all terms. So this sum itself is C of n into n plus 1 by 2. This is basically order of n square. This is the worst case time for the quicksort. Okay, now when is the best case? When is the best case for quicksort? So best case means it is partitioning, our partition is a good partition, that means our pivot is good, it is partitioning the array into half half. So n by 2, n by 2, in that case we are very much lucky. Okay. So our pivot is very good pivot, it is just the, it is choosing, it is putting in the middle like this. Okay. So in that case, what is the time complexity? What is the recurrence? Recurrence is, so we are dividing into two part, half half. So again we need to sort this part and this part. So 2 times Tn by 2 plus theta of n. This is the cost for the partition. Now what is the solution? This is again by master. This is the same recurrence as smart sort. By master method we know this is order of n log n. So this is good. I mean we are lucky if our partition is so good. But it may happen that our partition is not that much good, but it is partitioning like this. Some fraction over here, some fraction over here, say 1 by 10 into is to 9 by 10, or maybe 1 by 100 is to 99 by 100 like this. So then we want to see whether this is a good partition or bad partition, either we are lucky or unlucky. So suppose our partition is like this, then what is our recurrence? Recurrence is basically, so it is dividing into two part. This size is n by 10 and this size is 9n by 10. So T of n by 10 plus T of 9n by 10 plus theta of n. So this is the recurrence for this. Okay, so now how to solve this recurrence? So we will take help of recurrence tree to solve this. So this is our recurrence Tn by 10 plus T 9n by 10 plus Cn. So Tn is basically Cn. So Tn by 10, T 9n by 10. So this again will Cn. So this again will. So now this is our size. This is a problem. So recursively we are solving. So this is now the size of the problem n by 10, and again we are assuming the same partition will occur. So again for this sub problem it will be 1 by 10 is to 9 by 10. So if we assume that, then again it will be, so basically then we put n is equal to n by 10 over here. So C n by 10, and here it will be, so we put n is equal to n by 10, so n by 100, here T 9n by 100, and here we put just n is equal to, so C 9n by 10, and here T 9n by 100, and here it is T 81 n by 100 like this. So maybe one more step, Cn. So Cn by 10, 9 Cn by 10, and here it is Cn by 100, C 9n by 100 dot dot dot. It will end at T1, because once we reach T1 then it is sorted like this. So, this is basically C 9 n by 100, C 81 n by 100 dot dot dot, it is also end with T 1, but which branch will end first? This branch will which branch will end first, because this branch will end first, this branch will go a little long like this. So, now what is the time complexity for this? How to yeah, so this branch will end first, because this is going little faster and this branch is go little more. Okay. So, if we just the total time is the sum of all, if we just sum level wise, all level are in Cn like this. So, the time complexity, so what is the, if the height of this tree is left side is h1 and if this is h2, so h2 is little more than h1. So, we can have this Cn, this is the height of that h1, Cn log of n. Okay. Now, we can replace this by 2 and then log 10 base 2, that will be taken care by this constant. So, this is basically n log n. So, good. So, we are lucky. So, even the partition is not half, even the partition is some fraction over here, some fraction over here. This is 1 by 10, 9 by 10. Even we can try with 1 by 100, 99 by 100. Some little fraction if we can guarantee, then also our partition is giving us good result. So, it is a lucky case. Okay. Now, we will see the case where we are alternatively lucky, unlucky, and we want to see whether eventually we will be lucky or not. So, that means we are, this is a divide and conquer approach, we are dividing the problem into sub problems. So, suppose first step we are lucky, so and in the next step we will be unlucky. So, this is the lucky recurrence. So, ln, so now we are lucky, so that means it will divide into, but next step will be unlucky. So, this is the lucky step, and for unlucky step what we have, suppose now we are unlucky. So, that means it will divide into 0 is to n minus 1, but next step will be lucky. So, this is the unlucky recurrence. So, this is the situation, I mean we are lucky, unlucky, lucky, unlucky like this. So, we want to see eventually we will be lucky or unlucky. So, this is our equation 1, equation 2. So, we will put this here. So, ln is equal to 2. Now, this will be taken care by this part. So, this is basically unlucky recurrence is basically, so L of n minus 1 plus theta of n. So, this is basically L of n minus 2 minus 1 plus theta of n. We are combining these two. Now, this is just a lower ceiling or upper ceiling. This is n by 2 plus theta of n, because this minus 1 is just a ceiling. I mean, if we convert into integer part. So, this is basically give us the solution order of n log n. So, lucky day, lucky. Okay. So, even though there are many unlucky steps in the middle, but eventually we are lucky. So, if we can ensure that there is good number of lucky steps, then eventually we are lucky. So, this idea will help us to build a version of the quicksort, what is called randomized quicksort. Okay, so so in the randomized, so in our version of the quicksort, we are choosing the pivot element as the first element always in our partition algorithm, partition subroutine. Now we can choose any other element as a pivot, like if we choose middle element as a pivot. Okay, so we always follow the middle element as a pivot. So in that case, so in our case, first element as a pivot problem is if we take the if we take the sorted or reverse sorted array, then it is always choose the minimum or maximum. But in this case also, if we choose the middle element as a pivot always, then we can construct an input where we can put the middle element as the minimum or maximum. So one can come with some input where every time we are putting the minimum or maximum here. So for here like this. So in that case, our algorithm will perform badly, because we are choosing every time minimum or maximum as a pivot element. If we choose pivot is the middle, even though if we choose pivot as a second element, then also we can construct an input where we put every time second element is minimum or maximum. So that way we can always construct, we can always get and generate an input where our algorithm is performing badly. So to overcome this, what we do, we will choose the pivot element randomly. We will not declare before running the code which one will be our pivot element, so that no one can come with some input where our algorithm will perform badly. So that is the idea. So idea is to choose the pivot element randomly. Select the pivot randomly from the array. So pivot will be, so we have an array P to Q. So pivot element will be any one of this array, we can choose randomly. So this will be, this may be the pivot, this element may be the pivot. So they are equally likely. So each element can be a pivot with probability if there are n element 1 by n. So that is the version of the quicksort. So let me just quickly write the code. So this is the randomized quicksort. Okay, so now, so what we do, we choose a random number from this. So we choose randomly an index from this, and that is going to be our pivot. So this is suppose k we choose randomly. Okay, now we know a version of the quicksort where our, we know the version of the partition where our first element has a pivot. So we want to, if we want to use that, we can exchange this AP and AK. Now we call our partition algorithm, and then partition A comma P to K, and then we call this quicksort, randomized quicksort again, randomized quicksort A comma P to R, and then randomized quicksort A comma R plus 1 to Q. That is it. So only thing is we are choosing the pivot randomly. Since we want to use our old partition algorithm, we are converting, we are exchanging this and this, and then we are running our partition algorithm, and then it is returning R, X will be sitting there, the capital X, and then again recursively we are doing this. So what is the time complexity of this code? How we can analyze this code? Because this will depend on the partition. Okay. Now if we denote T of n is the runtime for this of this randomized version of quicksort where array element is n, then Tn will be written as in the functional form. This is the partition cost. If the partition is 0 is to n minus 1, then if the partition is 1 is to n minus 2, it is like this. So, in general, if the partition is k is to n minus k minus 1, if the partition is k is to n minus k minus 1, so it is n minus 1 plus theta of n. Theta of n is for cost for the partition subroutine. Now, this is in functional form. Now, this, so how to get this value? So, we can do some, we can take help of some indicator random variable. So, this is one, if the partition is k is to n minus k minus 1, 0 otherwise, and so and we are assuming the probability of each partition is equally likely. So, each partition probability is 1 by n. So, probability, so this is indicator random variable, and so expectation of this is 1 by n. Now, we can write T n in this summation of, because we cannot take the expectation just like this, x k into T of k plus theta of n. Okay. So, this is the expression. So, we do not know which partition will occur, but we know only one partition will occur. So, that is why we are taking help of this, only one x k value is 1, other is 0. So, now we are bringing this because of we want to take the expectation. Now, if you take the expectation, expectation will be this side. So, after some calculation we can see this will be n log n. So, the expected runtime of this version of the Quicksort is n log n. Okay. So, but we need some probability to prove this, which is out of which is not in the scope of this course. So, but anyway, so we must know we can show this expected value of T n is n log n. Thank you.